All right, so we are going to wrap up section 11.8 today. We have been talking about probability, and we've been looking at expanding binomials. Okay, so what I mean by that is if I gave you 2x plus 5y and I say take it to the 6th power, expand it out, could you do that? What would our first step be? Okay, look up Pascal's triangle, right? Your row that you're looking for starts with a 1 and then it has a 6, whatever your power is, right? So it's going to be 1, 6, whatever, yes? So that's the first number. Then what do we do? Okay, so then we would take 2x to each of them, right? And its power is 6, 5, 4, okay, going down. And then we take the 5y, and powers go reverse direction, yes? And you'd find all those pieces, right? Okay. And then if we were simply expanding it, we would write out all those answers, connect them with plus signs, right? And make it a big, long polynomial. Okay. We are using that expanding idea to help us find probabilities. So it says now you can apply that binomial theorem to binomial probabilities. To find the full probability distribution for a binomial experiment, you are going to expand this. Do you guys remember from yesterday what P and Q stood for? P was the probability of success, Q was the probability of failure. And it has to add up to 1. Okay, so P plus Q has to be 1. So the example that they've written out here, it says, suppose you guess on 4 questions of a 5-choice multiple choice test. Now what that means, okay, 4 questions means 4 trials, right? Each question is a trial, okay? So we have n being 4 for our 4 questions. Then it says it's a 5-choice multiple choice test. That means for every question you have choices A, B, C, D, E, right? You have 5 of them. So the probability of getting it right, if there's 5 to choose from and one of them's right, you have a 1 out of 5 chance of getting it right. Does that make sense? So our probability of success is 0.2, and we said they have to add up to 1, so our probability of failing has to be 0.8. Okay. Now, it says if we expand that, P plus Q to the nth power. So we have P plus Q to the 4th power, right? Because n was 4. When we expand, we take our Pascal's triangle row. That's the green numbers, the 1, 4, 6, 4, 1. Then we took P, and we said it starts out with its highest power. So 4, then 3, then 2, then 1, then none. And then we have Q's, and they go in the reverse direction. So no Q's in the first one, then 1Q, Q squared, Q cubed, Q to the 4th. Yes? So that's the expansion. And now we're just going to plug in our 0.2s and 0.8s. Okay, so P is 0.2, so all of the red P's turned into 0.2s, all of the blue Q's turned into 0.8s, and we simplified it. Okay. When you do that expansion, you are finding the complete or full probability distribution. You're finding all possibilities. So what is the possibility that I guess and I get all 4 questions right? Well, that came out to be this. So 0.16%. Okay? So it's a 4-question test. There's 5 choices to pick from for each question. If I completely guess on all 4 questions, I have a probability of less than 1% of getting them all right. Okay? The probability of getting 3 of them correct came out to be this. Probability of getting 2 correct, probability of getting 1 correct, and probability of getting none correct. Okay? So when you do that expansion, you're finding all the different options. You're not always asked for all of them. Okay? But if they want the complete probability distribution, then you have to find them all. So what they've done now is they've taken that information and put it in a bar graph. So here's our probability. Our highest probability was around 0.4. Okay, so we went up to 0.5 here for our axis, our y-axis. At the bottom, we have the number of correct answers. So we had equal probability of getting 0 or 1 correct. Okay, those probabilities came out to be the same. But it drastically goes down, right? Our probability of getting all 4 right was very, very small. Okay, so again, it's just a visual so you can see what's the most likely outcome. All right. Question 3 is going to mess with your minds a little bit, but we can handle it. We're intelligent. All right. It says, each hour, a cell phone factory quality control tests the durability of 4 randomly selected phones. Okay? So every hour, they're going to pick 4 phones to test. If more than one of them fails, quality control will reject the entire production for that hour. Okay? So there's unknown number of phones made in an hour, right? They're going to randomly pick 4 of them to check. And it says, if more than one fails, well, what does more than one mean? 2, 3, or all 4, right? Those are the things that we're looking for. If 2 phones fail, if 3 phones fail, or all 4 phones fail, they're going to say, throw out the whole batch, right? Throw out all the phones made that hour, something's wrong. We're going to start over. If in 1 hour, 95% of the phones made are acceptable, what is the probability that quality control rejects that hour's phone production? So where I said this is going to mess with your mind is that our success here is that the phones failed. Okay? They're asking us to figure out the chance of them failing. So when we talk about success, what we want to have happen, in this case, we want it to fail. Does that make sense? All right. So what do we know? They're testing 4 phones. What does that tell me? Is that P, Q, and X? Right? We need all of those to do our expansion? So if I go and grab 4 phones, I'm doing 4 trials, right? So that is my N value. Okay, now, how would I define X? X was the number of successes. And it said, if more than one fails, they're going to reject them all. And we said that meant 2 could fail, 3 could fail, or 4 could fail, right? So X is going to be 2, 3, or 4. We're going to have to do a few of these. Okay? Now, it says 95% of the phones are acceptable, meaning they work. So again, for us, success is that the phone doesn't work, right? So P is going to be 5%, right? If 95% work, then 5% don't work. So P is going to be 5% or 0.05, and Q is going to be 0.95. Yes? Okay. So we actually have to calculate 3 different things. What is the chance 2 phones fail? What is the chance 3 phones fail? What is the chance 4 phones fail? Yes? So we can do 3 things. We could expand the whole binomial and go all the way from 0 to 4, but we really don't care about the 0 and 1, right? We just want the 2, 3, 4. So let's look at what is the probability that there's 2 phones that fail. Okay. We said that would be NCX, right? So N was 4, 4C2, 2 phones fail. The number of failing phones is 2, and the probability that the phone fails is 5%. Well, if 2 phones fail, then that means the other 2 have to be good, right? They have to work, and the probability of that is 0.95. Yes? Okay. What about the probability of 3? We'll go back and do our calculations after we get these all set up. So this would be 4C3. All right. 5% chance that the phone doesn't work, and we want 3 phones to not work. 95% chance that it does work, and we want 1 of those. And then for the fourth one, 4C4, 0.05 to the fourth, 0.95 to the 0. Yes? Okay, so I'm going to pause the recording. You guys go ahead and calculate those 3 answers. All right, so we have our decimals calculated, yes? What do we get for this first one? I need to move things over a little bit here. Give myself a little more room. All right, what did we get? Okay, I'm going to have you leave it in decimals for just a sec. 0.013? 5?
Yes, 5.
Okay, and then for our next one?
4.75.
No, decimals.
4.7. 0.000475. There's 3 zeros. No, yeah, there's 3 zeros. I said 0, 0, 0.
All right, I wrote it wrong.
4.7.
0.000475.
Yes.
Okay, and then the last one?
0.0005.
How many zeros?
5. 65. There's 65 zeros? No.
Okay, so the probability that all 4 phones don't work is very, very tiny, right? This last number, very small. When it says we are going to reject the phones if 2 fail, or 3 fail, or all 4 fail, that means we want the probability of this, or this, or this, right? We have to add those up. So we need to take all these green numbers and add them up. Go ahead and do that. What? No, this is the probability that all 4, that you have to pick 4 that don't work. No. You're looking at what is the chance that this group of 4, none of them work. This is what is the chance that just 2 don't work. They are different. All right, when we add them all up, we get what? Okay, so about 1.4%. Yes? All right, so quality control is going to test 4 phones. There's only about 1.4% chance that they'll reject the phones for that hour. All right, and if you think about it, if 95% of them work, and if you think about how many phones they make, right, it's very unlikely that they're going to grab 4 that don't work. Okay. It can happen. All right. Question 3. I got it. Question 3. It says a multiple choice quiz has 5 questions. Each question has 4 answer choices. If you guess every answer, what is the probability of getting at least 3 correct? Okay. So let's identify N, X, P, Q. How many questions are we taking on the test? There's 5 questions. So N is 5? Each question has 4 answer choices, which means what? Each question has 4 answer choices. Okay. Why would P equal 0.25? So the probability, if there's 4 choices, A, B, C, D, right, one of them is right. So 1 out of the 4 is going to be correct. As a decimal, that is 0.25, and we said P and Q have to add up to 1, so we have 0.75 for Q. Okay? What is the probability of getting at least 3 correct? Well, if I did the whole probability distribution, what are my options? I get none correct, right? I could have none of them correct. I could have one of them correct, 2, 3, 4, or all 5 questions I could get right. Yes? This one says at least 3. That means we're looking for these. Yes? So we need the probability of 3, probability of 4, probability of 5, and then we'll add them up. Yes? All right. So setting it up with our NCX, we have 5C3, 5C4, and 5C5. Okay. Probability of success, we said, was 0.25. How many successes do we want for the first option here? 3. Next option, we want 4. Last, we want all 5. Probability of failing, 0.75. There'd be 2 failures if we got 3 of them correct. In our next one, we would have 1 failure, and in our last one, we have no failures. Okay? So again, I'm going to pause the recording, let you guys calculate those. All right, checking our numbers. For the first one, you should have about 0.087. Next one, about 0.014, and the next one, 0.0009. Yes? We add those 3 up. I got 0.10351, so about 10.35%. What are the ones that we didn't calculate?
0, 1, and 2.
Okay. If I did the complete probability distribution, so similar to the question we had up here, okay? If we took all of these numbers in this row and added them up, what would we get? We'd get 1, right? Because we're taking 100% probability and we're dividing it up into different options, okay? So my question for you is, in these last couple examples, we were calculating 3 of the possible outcomes. Yes? What if my question changed? Let's have it be, let's say we have 20 trials, all right? And I want the probability of at least 15 successes. Okay, whatever we're defining success to be. Okay? If I said out of those 20 trials, I want at least 15, which ones would I have to calculate? I'd have to figure out the way to get 15, right? The way to get 16, the way to get 17, the way to get 18, the way to get 19, and The way to get 20, yes? If I asked you to do the whole probability distribution, you'd have from 0 to 20, right? Don't worry, I'm not going to ask you to do that. But what if I changed the question? Let's pretend we already calculated all this, all right? We got an answer for at least 15. What if I now say, what is the probability no more than 14? What does no more than 14 mean? Okay. What are my options? 0, 1, 2, all the way up to 14, right? So if I have the probability of 0 all the way up to the 14, right? And I've already calculated above here 15 on up to 20, right? I don't have to find 0 to 14. If I know that this amount and all of this have to add up to 1, right? So I have an answer up here, we'll just call it x. If I know that that first answer is x%, my answer down here is going to be 1 minus that, right? So when you have a big distribution where there's a ton of trials and a ton of options, really think through, is it shorter to figure out the ones I want, or is it going to be shorter to figure out the ones I don't want and subtract it from 1? Does that make sense? So let's say I want, where's my extend here? Okay, let's say we have 30 trials, okay? So we have options all the way from none of it working to all 30 of it working, right? That's 31 things we'd have to calculate. If I say the probability of at least 5. At least 5 would mean 5 or 6 or 7 all the way up to 30, right? That's a lot of them. It's going to be shorter to take 1 minus the couple that we don't want. Does that make sense? So which ones do we not want? 0, 1, 2, 3, and 4. So here I'm calculating 5 up to 30, right? I don't want to do that. Here I'm just calculating these couple and subtracting my answer from 1. Does that make sense? Okay. So take a minute and put your summary down. We have done binomial probabilities, and now we've looked at binomial distributions. Okay? Maybe make some kind of notation of that formula. What does n stand for? What is x? What is p? What is q? Okay, take a minute and do that. Yes, we do have a test tomorrow. You will not have your notes. So make sure that you have your formulas down. I will give you Pascal's triangle. Okay, but you need to know how to use it with the formulas. All right, when you finish your summary, the assignment here is the day 2 one. Okay, I also need you guys to go into Schoology and give yourself a rating in that learning goals check-in